Hey guys, Michelle Glass here, and we are finishing here our part one of chapter 2 lecture series. And our topic for this presentation is pH. pH is represented with a lowercase p, capital H, and it actually stands for the percent of the hydrogen ion that is found in the solution. Now, pH is measured on a scale from 0 to 14, where 7 is considered neutral. So any numbers that are less than 7 to 0, so 6.99 to 0 is considered acidic, and any numbers greater than 7 up to 14 are considered basic. So that'd be from like 7.01 to 14, these are basic. Now, even though these numbers don't seem like they're big, a difference between 1 and 2 is really significant because your pH scale is a logarithmic scale. So you're actually changing by 10 when you're changing from a 1 to a 2. So it's pretty significant. Now, how did we actually derive a pH of neutral as being 7? This is based on the dissociation or separation of the water molecule in nature. So if you, well, not really in nature, because this is based on if you had a pure sample of water with nothing else in it, which you don't really find in nature, how much of that H2O is separating into a hydrogen ion and a hydroxide ion. Now notice that this is a reversible reaction. So in nature you see it together as a whole water molecule and then in its separate components. The key thing to pay attention to here is that hydrogen ion is highly reactive. It's just a proton with nothing in its electron shell. And then the hydroxide ion, the OH minus, is also going to be reactive because it is incomplete. The amount of free hydrogen ion in a pure water sample has a pH of 7, and so that's how we're getting our neutral designation. When we talk about our acidic pHs, remember those are low numbers, so a low pH corresponds to something that's acidic, and these numbers mean that you have a high concentration of hydrogen ion. So notice here that I've put my H plus in brackets. Those brackets are my shorthand for concentration. If you have something that's called a strong acid, it's releasing a whole lot of that hydrogen ion because instead of it being a reversible reaction, it's a reaction that's going in one way. So strong acids are going to fully disassociate, means separate. They're not reversible reactions. So you're putting a lot of hydrogen ion into solution. So a low number on the pH scale is something that's acidic. If it's acidic, you're contributing a lot of hydrogen ion into the solution. And remember, this is a reactive ion. It's a single proton. So I like to think about it as being willing to beg, borrow, and steal in order to complete that outer shell. So essentially, it's going to disrupt your body chemistry. The reverse of this is going to be on the lower end of the pH scale. So I shouldn't use the word low, on the higher end of the pH scale, so those numbers that are greater than 7 up to 14. So the larger the number is, the more basic or alkaline that solution will be. This is talking about having a whole lot of hydroxide ion. So your more alkaline solutions are going to have more hydroxide ion in those solutions. Now, the same is true for a strong base as for a strong acid. Strong bases will dissociate completely, fully releasing that hydroxide ion into solution. Hydroxide ion is equally disruptive to your body chemistry as hydrogen ion. So remember, we're looking at both sides, basically, of that water molecule when we talk about pH. How does the body deal with this? Okay, so our bodies produce and cells produce what are called buffers. And buffers are important chemicals because they can temporarily store hydrogen ion. If you're storing something, that means you can stick it in and you can take it out. So a good buffer is something that can absorb hydrogen ion out of solution and temporarily hang on to it, or release that hydrogen ion back into solution as needed so that you can so that you can modulate your pH of your body. These buffers are going to prevent very big fluctuations in pH from happening, because if you have a chemical reaction that releases a lot of H+, your buffer can just hold on to that. Or if you have a chemical reaction that releases a lot of hydroxide ion, you can release the H+, and then use that to create water. Okay, so that's it for part 1 of chapter 2.